Okay, so a lot of big words. We're going to say we're going to build algebraic models with algebra tiles. So really, we're working with algebra tiles. Okay. Now, I have 6 algebra tiles here. Okay. And what we're going to do is we're going to try to relate essentially what each of them stand for, and then we're going to use them in some problem-solving ways so that we can make sense of what it is they do. Now, we've talked about positive and negative numbers. Okay. Now, this one here, the green represents our positive tiles.
Yeah.
Okay. And the white are our negative tiles. Specifically, the ones at the bottom, this represents 1 unit. Okay? It doesn't matter what the unit is, it just represents. This represents -1 unit. Okay, so this is our unit tile. The second tile is an X tile, and it can be seen as like an unknown amount. Okay, so this is our positive, and again, this is our positive 1 unit, -1 unit. This is our positive, positive variable or positive X tile, we'll call it. And this is our negative X tile. And finally, this one seems complex, but we'll get to how we've gotten this in a minute. This is our positive X squared tile.
Oh, okay.
Okay.
It's a square.
Because it's a square, very good, and we're going to get into that. X square tile.
So it's 2 lengths, I guess 2 x's. So.
Multiplied, exactly. We're going to talk about that. So first thing we could say is, let's say I have a friend and he's a runner. Okay, his name's Dave, and he runs a kilometer every day. Well, we're going to say Dave runs a kilometer every day. We're going to represent 5 days of running for him, kind of in a chart. Okay, so I'm going to set up my chart here. These are the days, and these are total kilometers. It's lagging a little. Okay, these are going to be our days in total kilometers. Now, because we know the amount, and exactly we use 1 kilometer, which of the 3 tiles, or 6 technically tiles, do you think we're going to be using for this?
I think we'd be using the bottom tile.
Yeah, we're going to use that unit tile there. So I'm going to turn this into something for us. Infinite kilometer, it's called. Okay, it's going a bit slow, the computer, but. So we're going to take this tile over here. Let's scroll down here. And we're going to represent Dave's running. Oh, geez. There we go. It's going very slow. Okay. I'm going to pause this for a second. Okay, so like I said, we're going to represent those 5 days. So we have day 1, 2, 3, 4, and 5, and we're going to talk about the total kilometers he actually goes. Well, in day 1, how far will he ran?
1 kilometer.
So how many of these unit tiles will you use to represent that?
1.
Okay. Day 2, how far will he have ran?
2.
He'll have ran 2. So how many unit tiles will we
2.
use? Good. Very simple idea, right?
Yep.
So then day 3 will be how many tiles?
3.
Right? Day 4?
4. And day 5.
Okay. What do they represent? I'm just going to fill these in, but as I do, I want you to talk to me. What do each of these unit tiles represent?
They represent 1 unit. In this case, that's a kilometer.
Perfect. Exactly. Okay. So we're getting used to representing things using these unit tiles. 4.
Slow today.
Yeah, very slow today. 5. And that guy didn't even make it all the way down here. There we go. Okay, so we know they're going to represent our 1 kilometer, 2, 3, 4, and 5 kilometers. Okay, what I'm going to do is probably jump off this page. Might be the page is too laggy. Okay, that's fine. We've got that. Now let's say Dave. Go to the next page here. Dave, he goes skiing. So Dave, oh, this is better, goes skiing. And he actually goes cross-country skiing around the lake, let's say. So we got some big lake like this. And Dave starts at this point, and he cross-country skis all the way around the lake. Okay? What we're going to try to do is represent 3 days of skiing. Now, I have a problem. So, again, we'll set up that chart again. We have our days, right? And total distance. So days, we'll do 3 days. 1, 2, and 3. And total distance, we'll call this. Now, has Dave told us how far he goes?
No.
In fact, Dave doesn't know. You know, it's an irregular shape. He's unsure how far it is. So, let's go back to the other page. I want to know which of these tiles would we use to represent the unknown distance, do you think?
I'd use the X tile, the positive X tile.
Positive X tile, that's our unknown distance, right? Good. So we'll go back over this page. Okay, and we're going to represent this. We're going to use this to represent our total distance. So in day 1, how many tiles would we use?
1.
Yeah.
1. So X.
Okay.
Then it'll be 2X or 2 tiles.
Good. And then on day 3?
3X or 3 tiles.
Great. So he'll have traveled around the lake 3 times. He does this every day. He's quite the athlete, this guy. Okay. And the way we'd represent these are called polynomials, okay? So the very first one, we'll do it in blue beside it. This is just known as a value of x, or you could write a 1 in front of it. Okay, so we'll use 1x. How many x's are here?
2X.
2x. And how many x's are here?
3X.
So 3x, exactly. So that's how we use, that's how we would represent these numbers with these algebra tiles, okay? Okay, again, now let's say Dave has decided to build a garden. Okay, so Dave is building a garden. But he wants it to be the same on each side. Essentially, he's going to be building a square garden. He wants to build a square garden here. He's unsure what to go with to start. He doesn't know how big he wants it. So he decides to represent, he gets newspapers, okay? And one newspaper he uses to, he puts it on the ground to see how large of an area he wants to take up. So he knows a newspaper is essentially, let's say, when we spread it out, 60 centimeters, something like that. So when he goes back, he has a known amount. So we'll say as a unit, it's 1 unit of newspaper he's using, okay? So he's going to use these to represent his garden. Come on. Get rid of that. I'm going to copy it. Okay, so let's go back. So Dave takes one of his units here. Okay, he lays down 1 newspaper and he realizes, well, this newspaper takes up a distance of 1 this way and 1 that way, right? Well, when we're finding area is equal to the base times the length. In this case, it's 1 by 1. So what's the area of this garden?
It's 1 unit squared.
1 unit squared. Very good. Okay. Well, then Dave says, well, that's definitely not going to be big enough for what I need. So let's build a different one. I'm going to build it kind of like this. Because we said we want it to be a square, right?
Yep.
Okay. So we want it to be a square. Well, in terms of our units, this is 2 units wide and 2 units wide. So what would the area of this one be?
4 units squared.
That's right. We multiply the 2, so we have 4. Would we be able, using whole units, would I be able to get an area between 4 units and 1 unit? Could I make a garden that's a square with 3 units if I'm using whole numbers?
No, because 3 doesn't have a square root.
Yeah, that's right. Very good. So we can't really use those. So it's good to keep in mind that if we're building a square and we're actually getting values, these are kind of the only values we can really get. What would the next one be if we were to represent it by 3 by 3?
It would be 9 units squared.
Exactly. So if we were to set it up like this, and we wouldn't be able to get something in between. So, you know, Dave wants a large garden, but he realizes that he can only go up by certain increments, right? So it's kind of a trade-off. Well, do I want my unit to be 4 or 9? 9 start taking up a lot more room in his backyard, right? So we're going to represent it just like this. We know that it's 3 units wide, 3 units wide, okay? Which means the area of this is 9 units squared. Well, Dave says, scrap it. I'm just going to make an unknown amount, but I still want it to be a square. How can we represent his unknown amount? He doesn't know how long his base is going to be. He doesn't know how long the length of this is going to be. How can we represent that with the tiles we have?
We can use the positive x squared.
Okay, great. Let me just pull it out from here. I forgot they're right here. So let's do that. I'll pull out 2 of these. Excellent. So this will be our length, we'll call it. It doesn't have to be this wide. And this will be our width or base. Okay. So in other words, here's our length and here's our width. Okay. We know that when we multiply them together, we know that we do area. We go area is equal to length times width. Well, in this case, my length is x, and my width is what?
So your length would be x squared.
Good. Or my length, sorry, wouldn't be x squared. X times x is x squared.
Yeah, x times.
But what? Not my length, but my what?
Area.
Area. So we use this tile here to represent that area. And see how it's pretty much the same size here? They fit pretty nicely together. They represent, that would be our area represented. So it's representing a larger area when we do this. Okay. Now finally, there is a last one I do want to talk about. Dave has decided that he's not making a garden. He's going to make a greenhouse. So Dave's greenhouse now we're talking about. House. Okay. Well, a greenhouse doesn't just sit on the floor. It has several dimensions to it. Okay. So we're going to try to represent this. The tiles aren't the best, but I'm going to try to represent it with them. Let's see. Dave, again, is a very indecisive person. Doesn't know how big he's going to make his greenhouse. He knows it's going to have a base. It's also going to have a height. It's going to have something else to it too. Well, he's decided that he wants this to be a cube. Okay. Dave's greenhouse is going to be a cube, which means the length, the width, and the depth are all the same. Okay. So I know these look funny, but this is what we're talking about in terms of representing something that's a cube. It's 3-dimensional. Okay. Now we don't have a tile for it, but we're going to try to imagine this. So here's the face of it. It goes back about that far. Okay. So here is Dave's greenhouse. Okay. He's decided to make it a cube. Now I know it doesn't look exactly like a cube in terms of its depth. But in other words, this is our unknown amount, x, right? And to find the volume, the volume of this cube, we would take normally the length, and they have different names for these things, right? There's we usually, sometimes they call this might be the length. This is the height sometimes, so length.
And that's the width.
Yeah, width. Another word that they tend to use when you get in high school is called depth. How deep does it go? Okay, all meaning the same thing, times depth. Well, in this case, he has no idea what he's going to make it, how tall, right? Let's say his main requirement is the height. Well, if he wants to be the cube, the length and the depth have to be the same height of his cube. Okay, so in terms of figuring out the volume of this, well, the length is a unknown amount, and we've used the tile to represent that. Okay, the height is an unknown amount, we've used the tile to represent that, and the depth is an unknown amount. When we multiply these together, do you know what we're going to get as a volume?
Yeah,
what
x cubed.
X cubed, x to the power of 3. So let's see. And the idea of that now, I can't quite use it with this. Here's our face, right? And this is the face of the greenhouse. Well, think of it like when we're trying to find that volume, because it's 3-dimensional, we're taking sections of it. So this is the first, face that we use. Then we use another one like this. So we're slicing, it almost looks like a slice of bread. And this is a way to look at volume. We always take the face value, and in this case it's a cube. Right? We take this face value and we just put it all the way back. Okay? And that's essentially what our volume is. But we represent it, you're right, with x cubed. So I'm going to give you some expressions, right? And maybe at the side he decides that he's also going to get a small doghouse. Okay? So Dave goes, you know what, I want a small doghouse on the side, and I want it to be, I don't know, what's a good value? 2, 4, 8. He's decided this doghouse is going to have a volume of 8 units cubed. What can you use to represent these 8 units?
Well, 8 units cubed, that's also 8 is 2 to the power of 3.
That's right. So let's go back to our unit values because we want to represent them with algebra tiles. Okay? So in other words, right, and I'm going to move this to the top. We got this algebra tile, we're going to use this to represent it. You know, he's going to have, because he wants this to be a cube too,
Yep.
2 wide, 2 high, and then again, it's kind of hard to represent it in terms of depth, but
Yeah.
his depth is, we'll kind of turn on an angle, doesn't quite do it, because these are 2-dimensional, right?
Yeah.
But those are going to be our depth too, okay? So essentially, you're right, he's going to have a 2 by 2 by 2 for his doghouse. Well, let's say he had to get all the material for this stuff. We don't know how large the volume is going to be, so his material is going to be x cubed for everything. But he does know how large the other part's going to be. So how can I write this as an expression? X cubed, what else will he need? He'll need 8 units, right? So the total volume of stuff or materials he'll need is x cubed plus 8, right? Well, in order to represent that using algebra tiles, and we don't have an algebra tile for cubed, right? So let's actually refer back to his garden. We'll jump back one. Let's say he has a garden and that doghouse, okay? Well, in this case, we can represent this. Our garden is x squared, is an unknown amount, and then we know we have 8 units in terms of material he needs. So to represent this with our algebra tiles is one of those, and then 8 of those, exactly. So we set this up. I'm going to make a bunch of them. So we have 1, 2, 3, 5, 6, 6, 7, 8. And that's how we can represent plus 8, x squared, this is the tile, plus 8 units. Okay? So this is how we can kind of represent all of these things using our algebra tiles.